Okay, so good evening, one and all. Before starting today's session, just let me recall what we have done in the last session. So yesterday we demonstrated you how to perform the geometry optimization, right? We took ethanol as an example. Then we have explained each parameters like how to choose the basis set functionals, then spin, charge. So what are the different types of calculation when we need to do the time dependent and when we need to perform the time independent DFT calculation, then how to submit the job. So all those kind of things we have discussed. And then once the calculation was done, we demonstrated you how to do the analysis of your geometry optimized calculation, like how to plot the your optimized curve or RMS gradient or RMS force curve or like displacement curve. Then how to calculate the Mulliken charges, how to save your optimized structure, then how to visualize like different parameters like bond length, bond angle, and then forces on each atoms, right? And then we also learned how to calculate this electron density surface, then how to analyze that electron density surface, then how to calculate this electrostatic potential diagram, then how to do the analysis of that electrostatic potential diagram. Okay, that is what we have covered in the last class. So in today's session, we are going to cover a lot of things. So first we'll discuss how to calculate the IR spectra. Okay, so first I will demonstrate you how to do the IR spectra calculation. Then we'll go for the Raman spectra calculation. Then we'll go for the VCD calculation. Okay, after that we'll go for NMR calculation. Then we'll go for UV calculation and ECD calculation. So today we are going to cover the 6 type of calculation. Okay, so without further delay, I will start the session. Okay, I hope so you are following me. So whatever I'm going to teach you, I think you are getting it. So please try to do simultaneously with me. Okay. So now to perform this frequency calculation, just first open the software. Okay. So you just double click on this icon. So it will open both your Gaussian software and your visualization window. Okay. So let me fix it here. Okay. So before submitting the calculation, you just keep in mind that, so whenever you are going to perform any kind of calculation, like frequency calculation or energy calculation or NMR or like scanning calculation or IRC calculation in DFT calculation, the first thing is you need to optimize your structure, right? Once the optimization was done, you will get the optimized structure, and that structure you need to use for the further calculation. Let's consider if you are going to perform the frequency calculation. So first you need to optimize your structure, then you have to perform the frequency calculation. Or let's consider you are going to perform the energy calculation. First you need to do the optimization, then you need to go for the frequency calculation. So yesterday only we have optimized our structure. So whatever the optimized structure is there, so we are going to use that structure for the frequency calculation. Okay. So now to calculate the IR spectra, first you need to upload your optimized structure. So how to upload the optimized structure? You already know that. Once the calculation was completed in Gaussian, you will get the 2 output file. So one is the logarithmic file, another one is the CHK file, right? Checkpoint file. So to perform further calculation, you need to use the logarithmic file. Okay. So all of you just open logarithmic file. So to open the file, either you just click on the file menu and you just click on the open. Otherwise, directly you just click on this open option. Okay. So you just click on this open to, and it will be redirected to your file manager. And now you just navigate to the folder where your logarithmic file is present. In my case, it is present on the desktop. So I am going to open this logarithmic file. This one. So ethanol.opt.log. That is logarithmic file. So I hope all of you know that how we got this file, right? Yesterday we did the calculation and we are going to use the same logarithmic file. Just select that file and you just click on the open. So now the logarithmic file is opened. So now we can submit the calculation. Okay. So once you open your logarithmic file, you just right click and just click on the calculate option. Otherwise, directly just go to the Gaussian window here and you just click on the calculate. So once you click on the calculate, you will get this window here. You just click on the first option, that is Gaussian calculation setup. Okay. So there is a question from Yamini. Do we need to check the read coordinates options? No, not needed. Okay. For calculation, it is not needed. Okay. No need to check it. Okay, so once you click on this setup Gaussian calculation setup, you will get this window, right? Already you are aware with this kind of interface. So now here you have to give your input parameters. So according to your calculation, so what exactly you want, so you need to provide the input parameters. So how to provide? First, you have to choose the job type. So first you click on the job type. So here, if you click here in the drop down menu, there is many options are there. So according to that, you have to choose so which option is needed for your calculation. Now we are going to perform the frequency calculation. Okay, then I will select the frequency. So let's consider if you want to perform the optimization of frequency directly, in that case, you can use this opt plus frequency. In that case, first it will optimize your structure, then you will perform the frequency calculation. Okay. So now I just want frequency calculation because already optimization was done. So I will just click on the frequency button. So now the job type is frequency. Okay. So here, once you click on the frequency, there are many options there. So now let's try to understand then how to choose. The first option is compute Raman. So compute Raman means like, do you want to calculate the Raman spectra for your structure? Okay, if you go with the default option, sometimes it will calculate, sometimes it won't calculate, okay, depending on the structure. But like there are three options like default, no, yes. If you want to calculate the Raman, then you just click on the S button. If you don't want Raman spectra, then click on the no button. Okay, if you click on the default, sometimes it will calculate, sometimes it won't calculate. Okay, so for this calculation, what I will do, so instead of doing the calculation separately, IR, Raman, and VCD, I will do all the calculation in one stretch. Okay, so simultaneously, I will calculate the IR spectra, Raman spectra, and VCD spectra for the ethanol. So in that case, what I will do, you just click on this compute Raman here and choose the yes option. So now it will calculate the Raman spectra for your compound. And the next option is like save normal mode option. You no need to worry about that. Okay. And then the next option is like compute VCD spectra. So if you want to calculate the VCD spectra, then you just click on this button. So it will calculate the VCD spectra. Okay. So after calculation, I will explain you detail like what is exactly IR, what is Raman, what is VCD spectra, then how to analyze that. So now you just remember. Okay. So I am going to calculate the IR spectra, Raman spectra, and VCD spectra. So below that, there is like compute Raman optical activity spectra. If you want to calculate the Raman optical activity spectra, then you just click on the yes button or no button. But now in this calculation, I'm not going to do because Raman optical activity, it will take some time, more time. So I'm not going to calculate it. I'll just give the no button. But you just keep in mind that if you want to calculate the Raman optical activity spectra, you just click on the yes button. Okay. But I don't want to because it will take more time. And then no need to worry about that. So here also no need to worry anything. And here once you given the, if you want to give some normal modes, you click on the select mode. And if you want to give like specific any kind of modes, then you can give, but not needed. You just go with the default option. And there is like one more option is there here. Anharmonic correction. Okay. So there are two options, right? Whenever you talk about this IR spectra or Raman spectra, so we'll talk about like two, like harmonic IR spectra and anharmonic IR spectra. So now you may get the question, like what is the difference between this harmonic and anharmonic IR spectra? Okay. So here in harmonic, what happens? Now for this demonstration, I'm going to calculate only harmonic because if I select the anharmonic, later I will tell what is the difference here. So if I go with the anharmonic correction, like if you want to calculate both harmonic IR spectra and anharmonic IR spectra, so in that you have to activate this one. Okay. Even if you have like specific number of harmonic modes, if you want to calculate, you just check this box and you can just specify how many modes you want to calculate. Okay. But I don't want to specify here. Even I don't want to calculate the anharmonic correction. The only reason I'm not selecting because it will take more time to perform the calculation. Okay. So that's why I don't want to calculate here. I will just deselect it here. Now let's try to understand like what is the difference between harmonic and anharmonic. Okay. So in harmonic IR spectra, it is a simplified model. So simplified means in the harmonic principle phenomena, it will assumes that the molecule vibrates like a ideal spring. I hope it is clear to like what is ideal spring. Okay. So here the vibrational energy levels are equally spaced. When there is a harmonic IR spectra, the vibrational energy are equally spaced. And usually this your harmonic IR spectra will give the sharp, very distinct peak in your IR spectrum. So it shows only the main vibrational transition. So main vibrational transitions means the fundamental bands, right? So when we talk about the vibrational transition, usually we'll talk about the three things. Like one is the fundamental bands, second one is the overtones, and the third one is the combination bands. But your harmonic IR spectra will give the only information about the fundamental bands. It won't give any information about the overtones and combinational bands. So if you want the information about the overtones and combination bands, in that case, you need to calculate the anharmonic IR spectra or anharmonic Raman spectra. So in anharmonic IR or Raman spectra, what happens? It is like realistic model, whereas your harmonic is simple model, like very simplified model, like it considered it as a ideal spin kind of vibration. But anharmonic is, it is like a very realistic model. So it considers that the real molecular vibrations are more complex than the ideal spring. Okay. So here the vibration energy levels are not equally spaced. Equally, like evenly, they are not evenly spaced, but in terms of like harmonic, the energy levels or the vibrational levels are equally spaced. So that is the difference between the harmonic and anharmonic. And if you calculate the harmonic IR, so you will get only the information about the fundamental bands. So those are main important. And if you want the information about overtones and combination bands, in that case, you can calculate the anharmonic IR spectra. So where you will get the information about the fundamental bands, overtones, and combination bands. I hope it is clear to you. What is the difference between the harmonic and anharmonic spectra? So similarly, you can calculate the harmonic like IR spectra, anharmonic IR spectra, harmonic Raman spectra, and anharmonic Raman spectra. But now I'm not going to calculate. If you want to calculate the anharmonic spectra, you just select this one. So if you select this option, it will perform the calculation, but it will take a lot of time. So in the live session, I can't show it. So that's why I'm not going to do that one. Okay. I hope it is clear to you when to use this option. And the next option is like compute projected frequencies. So here compute projected frequency means here what if you select this option, what it will do? So it will calculate the frequency of like individual items. So individual items which are present in your molecular system. Okay. Let's consider if you calculate normal frequency calculation, what it will do? So it will give the overall frequency, overall vibration. So what is the total? And if you want to, if you click on this compute projected frequencies, so it will individually calculate what is the frequency of like oxygen, hydrogen, carbon, like these are like projected frequencies. Even when you talk about like DOS and band structure, so they will calculate two types, like normal band structure, then projected band structure. Like normal density of state, then projected density of state. So when we talk about like normal band structure or density of state frequency, it will be the overall. So it will give the overall collectively how it was changing. But when you talk about the projected, so it will give the information about the particular atoms which are present in your molecule. So that is the difference. And even if you choose this one, so it will take time because it has to focus on each atom individually to calculate their frequencies. So again, it will take more time. So I'm not going to choose this one. So because I'm just going to perform the basic calculation, what is needed. Okay. I hope it is clear to you. So how to select the option in under your frequency calculation. So once you are done with this, you just click on the method tab. Once you click on the method, so similar thing. So you already know this one, how to choose the different parameters under this method tab. And yesterday only have explained each parameter. And here you no need to give anything. By default, it will select. See, everything is selected. Ground state, DFT, default spin, B3LYP, 631G basis set, plus diffusion function, DNP, polarization function, charge zero spin, like multiplicity, singlet. How it is selected? Because we are using the output file of the optimization calculation. So these are the parameters what we used for the optimization of this molecule. So we are taking the output file of our previous calculation. So software by default, it will detect the parameters we considered during our previous calculation. You don't need to change anything. Okay. You just use the same parameters and you can use it. Okay. So here also no need to go for, there is one more option like multi-layer ONEM model is here. Here also you no need to consider this one. So like it is like only some kind of like if you want to perform some kind of like specific calculation, if there are like layers in your molecular system, then only you have to choose this one. So now we have only a single molecule, right? Let's consider you are going to perform the DFT calculation of like adsorption studies, surface adsorbent interaction, or if you are going to study this enzymatic reaction modeling, or if you want to going to study the catalysis or large biomolecules, in that case, we are going to use these options. Okay. So like if there are multiple layers are there, like layer 1, layer 2, layer 3, in that case, we are going to use the multi-layer onion model. Okay. So here what happens if in this model, if you choose this model, see here, I will just show it here. So once I activate this model, here you will get the 3 options: high level, higher layer, medium layer, low layer. So here, by using this option for each layer, you can use the different parameters. See, if you deselect this option, for all the 3 layers, you are going to use the same kind of input parameters. But if you activate this option, you can use the different parameters for different layers. For high layer, you can use the like higher level of functionals or basis set DFT calculation. Okay. So for medium layer, you can just treat with the moderate level of quantum method. For low level like layer, you can treat with the low level quantum methods by using that one. Okay. So when it comes to like layered structure, usually in terms of like solids, it is not applicable for like organic molecules or inorganic molecules or like metal complexes. When it comes to this solid state studies, surface analysis, in that case, this option will be useful. Then you can just click on, because now these 2 layers are deactivated because we have only one layer here, only one structure. So that's why it is deactivated here. Now you may get the question like how to add the layers. There is an option is there. See, layer option, you can use this option. You can add the layers, and there is a periodic boundary option is there. By using that, you can define the periodic boundary condition of that. Okay. So now just deselect this one, and here no need to select change anything. Now let's just click on the title tab. So now just give the title of your calculation. So this is a frequency calculation. I will give ethanol underscore frequency. So ethanol underscore frequency, give the title, and we just copy this one. Just copy it, Control C. And now we just click on the link button. So here also no need to do any changes. So even the only thing is if you want to perform your calculation faster, in that case, you can just increase the memory limit and you can share the number of processors. Okay. So you can just click here. So there is a question from Amini. Sir, is this multi-layer option applicable for nano materials? Yes, it is applicable. It depends on like how many layers you are going to take. In that case, it is dependable. If you are going like only one nano layer of your one layer of your nanomaterials, then it is not needed. Okay. Even let's consider, even if you are going to use like double layer or multiple like 3-layer system, you are doing the DFT calculation. For all the layers, if you want to use the same types of parameters, then no need to use that onion model option. But if you want to give the different parameters for all the different layers which are present in your system, then only you have to use that option. I hope it is clear to you, Yamini. Okay. So I'm talking about here, right? Yes. So memory limit and shared processor. If you want to increase the speed of your calculation, you can just change it here. And sometimes what happens, even if the memory level, let's consider, you have taken the very big molecule for the calculation. And whenever you're going to submit the calculation, the calculation will die, it won't run. So for that, this memory limit will be the one of the reason, because the memory required for that calculation is very high, but you have given like very less memory. In that case, it will go. So in that case, you just better go with the default option. Automatically, it will decide. So how much memory it want, it will take it automatically. And the next one is the shared processors. Okay, if you click here, so there are number of processors are there. According to that, you can select it. But if you want to finish your calculation faster, you can use all the processors of your system. Then it will finish as soon as possible. But I will go with the default option here. No need to change anything here. Then you just click on the general. Here also no need to do any changes for the frequency calculation. And then, yeah, here if you want to calculate this polarizabilities, then you can select this one, compute polarizabilities. If you want to get information about the polarizability of your molecular system, then you can choose it, but I don't want it here. And the guest tab, so here no need to do anything. Periodic boundary condition is applicable only for the solid materials. Then salvation. So if you have like, if you want to perform these studies in specific solvent medium, then you can choose the solvent. Already you know how to choose. You just click here and you can go to the model, click on the default, and you can just do it here. Otherwise, these are the different solvent models. You can choose it here. But for this calculation, I will go with the gas phase. I don't want to consider any kind of solvent. And then you just click on this one, add any other additional inputs. If it is there, you can add it, but nothing is there. And you just click on the preview option. So once you click on the preview option, so it will create your overall input file. So what kind of parameters you are going to use, what kind of calculations, all the XYZ coordinates of all the atoms which are present. And this is the charge, and this is the multiplicity system. This is your calculation type. Okay. So there is a question like, what is the pop option? So pop is like population. We'll do like population type of option will be there. Like if you want to do some kind of like Hertzfeld analysis, okay, then this natural bond orbitals calculation. In that case, we'll use. Okay, so I will tell when we do this natural bond calculation. In that time, I will explain how to use this pop option. So now it is not needed. That is like population option. I hope it is clear to you, Amini. So there is a question from Samruddhi, how to know how many processors are there in system? You just go to your system settings, okay? You just go to the system setting, and from there you can find out how many processors are there in your system. It's very easy. After that, you just click on the preview button and it will give the, I hope it is clear to you, Samruddhi. Okay. Okay, so this is input file, and you can just, once it is ready, you just click on the submit button. And see, in the previous calculation, we have given the additional keywords, right? Pop is equal to full, right? So, but here no need to give that pop is equal to full, because see, without giving that additional keywords, automatically it was taken. Why? So because in our previous calculation, we have already used this keyword. So from that calculation, automatically it will take. You no need to give once again. So once it is done, you just click on the submit button. Once you click on the submit button, you will get this pop-up. Like you must save a Gaussian input file before you submit. So would you like to save an input file now? You just click on the save button. So once you click on the save button, it will ask you to where you want to save your file. Okay, if you have like some kind of like specific parameters, like folders, in that you can just choose that folder, but I want to save it on the desktop. I don't want to change. Just give the name. Okay. So whatever the name you have given, there we have copied, right? Title, you just paste it here, control ethanol underscore frequency. And just click on the save button. So once you click on the save button, it will ask you to submit the calculation to the Gaussian. You just click on the yes button. So once you click on the yes button, it will submit the calculation to the Gaussian. See, now the calculation is going on. So it will take some time depending on your system specification and the size of your molecular system and the basis set functions you have used. Okay. I think it will take like 2 to 3 minutes. We'll wait until the calculation will complete. So there is a question from Samruddhi, which kind of additional information we can add? So it depends on what kind of calculation you are going to do. Like if you want to mention some kind of like specific temperature, specific pH calculation, if you want to use some kind of buffer, in that case, you can give those kind of additional parameters. Okay. I will show how to do DFT at different temperature, pH, pressure. I will show it later. See, in my case, the calculation was completed. So once the calculation was completed, you will get this kind of message. So Gaussian job completed. Do you want to close the Gaussian windows? You just click on the yes button. So before going ahead, so just confirm me how many of you completed the calculation successfully. I think those who are using the ethanol, it won't take more than 2 to 3 minutes. But if you're using some other molecules, larger molecules, it will take, because for frequency calculation, it will take a lot of time. Optimization, okay, frequency, it will take more time. So those who are using ethanol, you just mention it in the chat box, whether the calculation was completed or not. How many of you completed? Suruchi completed, Jessil completed. Yeah, I mean, it's still going on, okay. So there is one. Masida, okay. See, actually, the thing is already your Gaussian is running. You are submitting the job again and again. Let me see it here, like Mazida. So because see, it was telling that. So whenever you're getting the error, you just read the message, what exactly it is. So because already your Gaussian calculation is going on, so you are submitting one more calculation. That's why it is telling that. So it can like perform only one type of calculation at a time. So that is that. So Bhargav completed, Vijayalakshmi completed, Amal Shashi completed. Okay. So I'll just wait for 30 seconds. Just once your job got completed, you just mention it in the chat box. So we'll proceed with the result analysis. So is anybody facing any kind of technical issues? If anybody facing, just write it in the chat box. And if you're getting any kind of error, you just upload it to the screenshot. Okay, so we'll proceed with the analysis part. So once the calculation was done, you will get this kind of message. You just click on the, so Muhammad Ilyas uploaded one file. So I did not understand. You uploaded the CIF file. Okay, you just click on the, yes, please write your question in the chat box. Okay. So you just click on the yes button. So once you click on the yes button, so this window will pop up here. So here also, once the Gaussian calculation was, whatever the calculation type it is, once the calculation was done, it will create two files. One is like logarithmic file, another one is a checkpoint file. So we have to do the analysis first by using the logarithmic file. Select the logarithmic file, deselect this your checkpoint file, and click on the open button. So once you click on the open button, see it will open the structure generated after the frequency calculation. There is no change in the structure, but you can just visualize your frequency log file. So now by using this file, you can do the analysis. You can generate the IR spectra, Raman spectra, VCD spectra. Okay. Like you can find out whether is there any kind of like imaginary frequency is there or not, all those kind of things. How to do that? Just right click, then go to the results. Okay. And first click on the summary. So it will give the summary full chart here. So again, same thing, it will give like what kind of calculation it is, spin state, salvation energy, total energy, okay, RMS gradient. These values will be similar like from your previous calculation. And here it will be like it is giving the imaginary frequency will be 0. You just keep it in mind that if you are getting any kind of imaginary frequency, then your calculation is not correct. It should be 0. Okay. So if you're getting any kind of imaginary frequency, it indicates that your optimization calculation or frequency calculation was not done properly. Okay, you just make sure that. And it will dipole moment also previous one only. This is a polarizability. Okay, it will calculate polarizability, and this is a polarizability value in terms of atomic unit. The remaining everything is common. And yesterday, after performing this thermoelectric, like thermoelectric properties, this was like not activated, right? It is deactivated. But now after the frequency calculation, so this button tab got activated. You just click on this thermo property. So once you click on this thermo property, see many properties it has calculated. So the first is imaginary frequency. Is there any imaginary frequency or not? Okay. So if there is no 0, if any imaginary frequency is there, it will show how many imaginary frequencies are there. Then it is telling that at what temperature this calculation was done, at room temperature, 298.15 Kelvin. So what is the pressure it was considered? Like 1 atmospheric pressure. Like if you want to perform the same calculation at different temperature and pressure, in that case, you can go to the additional inputs. There you can assign that. Then frequency scaled by factor, it is 1. No, and this is like overall electronic energy of your system. So this is the 0 point energy correction. How much energy correction was done? Okay. So this is like thermal correction of energy. And this is a thermal correction to enthalpy. And thermal correction to the free energy. Okay. So it is like electronic energy plus 0 point energy, how much you are getting. Okay. And this one is electronic energy plus thermal energy collection. They're like addition of like thermal enthalpy and thermal free energy collection. There are different parameters are there. And total energy is like thermal energy, how much you are getting. And the heat capacity value, like if you want to find out what is the heat capacity, you can easily find out by performing the frequency calculation. So this is the heat capacity of your system. And here you have the all like unit, which unit it is represented here. And if you click on the entropy, so it will give the what is the entropy of your system. See that we are getting many properties here, and you can find out the same all this information by opening your logarithmic file in Notepad also. I hope it is clear to you. And you just click on this opt button. So it is like similar to your previous calculation. So whatever the optimization was done, from here only it was like continuing. I hope it is clear to you. I will just close this one now. And now just right click here to visualize the IR spectrum, to visualize the different frequencies. You just click here. So click on the right click, go to the results, and you just come down here. Now just click on the vibrations. Okay. Just click on the vibration. See, once you click on the vibration, you will get this window. So in this window, you have the information about all your like IR spectra, Raman spectra, and VCD spectra, everything. See here, you can observe this table. So in the first line here, first I'm going to talk about this table. See here, for example, if you calculate only IR spectra, you will get only these two columns, these three columns. First one, modes, frequency, and infrared. If you calculate only the VCD spectra, in that case, it will give only both this IR and VCD. If you calculate only the Raman spectra, in that case, you will get the IR and Raman. These three columns is related to the Raman spectra calculation. This column is related to your VCD, and this is related to your IR, and this related to all the spectra. Now let's try to understand what exactly these are. The first one is the modes. So modes is nothing but the vibrational mode number. Okay, so it helps us to identify the specific normal mode of vibration, right? Okay, so you just select there is a different modes are there. After that, there is like frequency. Okay, your frequency indicates that the vibrational frequency of each mode. Okay, so it indicates how fast the atom vibrate in your mode. So see, the first mode, the frequency is 241.35, like that. And next one is like infrared. So infrared indicates that intensity of the mode. Okay, so that is the intensity, because in the frequency, like IR spectra, what we will consider along the x-axis, we will consider the wave number. Along the y-axis, we will consider the intensity, right? So that is what it is representing, the frequency, and this is the intensity. Next one is the VCD, rote STR is there. It indicates that vibrational circular dichroism. That is a VCD full form, right? So here rote means rotational, STR means strength. So VCD rotational strength. So here the value is equal to 0. So later I will explain what exactly this value indicates, that you just understand these columns. And the next column is like your Raman activity. Okay, so these are the Raman scattering activity of the all the modes which are present in your material. And here we have the like dipolar P and dipolar U. So this is very important. Many people will face problem to understand this one. So what is like dipolar P and dipolar U? Usually when you calculate the Raman spectra, so we'll focus, even if you, I think if you are like studied your theoretical part of Raman spectra, there we are going to use like a depolarization ratio. In that case, we are going to talk about this dipolar P and dipolar U. Now let's try to understand what exactly this dipolar P and U. So in Raman spectra, what happens? Let's consider when the laser hits the molecule will vibrate, right? And once it will vibrate, and it will scatter the light. I hope you know what is scattering of light. Okay. And here, when it scatters the light, that scatter light can go in different directions, right? So it can go in any direction and have the different polarization. Okay, so when it can go in different direction, it means that it has the different polarizations. So polarization is nothing but, in simple word, it is the direction of the electric field. Okay. In simple words, that is the direction of polarization. Now let's try to understand properly like what exactly this polarization do. So we know that light has an electric field, right? So that can vibrate in a certain direction. Okay. So if the most of the scattered light vibrates in the same direction as the incoming light, then it is known as the polarized light. Okay. So otherwise, if it vibrates randomly in all direction, then it is known as the depolarized light. I hope it is clear to you. What is the polarization? Polarization is nothing but the direction of the electric field is collectively known as the polarization. So in that case, if you are like, what exact the difference between the polarized light and depolarized light? So when the light scatters, if it like move in the same direction as like your light moving, then it is known as the polarized light. So if it is like moving in a different direction, In that case of light is known as the depolarized light. That is the difference between polarized and depolarized light. Now, how this dipolar P and if you want to tell the full name, it is like polarized, dipolar. This one is unpolarized, or you can call it as depolarized, unpolarized, dipolar ratio. It is polarized, dipolar ratio. Okay. So these values for the polarized light. Okay. So whatever the calculation, like there is first mode is there. So for first mode, this is the depolarization ratio for the polarized light. So this is the depolarized ratio value for the unpolarized light present, which is responsible for the first mode. Okay. So because when there is a vibrational mode, so it has both, right? It has like polarized light and depolarized light. And it will calculate the what is the depolarized ratio for all the both polarized and depolarized light, which is related to your mode. Okay. So this depolarized P, it tells us like how much the scattered light is vibrating in the different direction from the incoming light. So usually these values are ranging from like 0 to 0.75. Okay, the scale, if you want to give the scale here, it is like 0 to 0.75. Okay, so here usually like 0 means the low value. The low value indicates that most of the light stays in the same direction. When it is in the same direction, the vibration is symmetric in nature. And if the value is equal to like 0.75, it indicates that most of the light goes in different direction. That is, the vibration is asymmetric in nature. So that is the meaning of these values. As the value is near to 0, it indicates that is like vibration is symmetric. Because when you talk about the IR spectroscopy, also it is like due to the vibration, right? There is a different types of vibrations are there. Symmetric, asymmetric vibration, like bending is there. So we'll talk about different types like wagging, twisting. So there are different types of vibrations are there. So here like we'll talk about the symmetry. Similarly, like how we are considering it for like polarized light. So it is like similar to your dipolar P. The only difference is it will consider the unpolarized incident light. So that is the difference. I hope it is clear to you. So what is the meaning of the each column in this table? Okay. Now let me open the spectra. Now let's try to plot all the three spectra like IR spectra, Raman spectra, and VCD spectra. So do you have any questions so far in this table? If you have any question, please write it in the chat box. So there is a question from Mohammed Ilyas, like today I was working on 2D transition metal structure to optimize it. So but the optimization failed and gave an error. What should I do, sir? Yeah, see, you have taken the transition metal structure, right? So which structure you have taken? Tell me the exact name of your compound. Okay, and tell me the parameters. What parameters? Because when you take these metal complexes, you have to use a multiple basis set. If you go with a single basis set, it won't work. So that's why don't do with your material. First, try to learn step by step. Okay. Even I will demonstrate you how to do it for the transition metal complex also, but try to do step by step. Okay, there is a question from IT. I did not get the Raman activity column. Okay, so nothing. Okay, you just understand that this is a Raman activity. Okay, so these values are corresponding to Raman activity. Okay, I will explain. While explaining the Raman spectra, I will explain. Otherwise, tell it now only. For example, here you are getting the values, right? So like how much light is scattering in that mode? Like consider mode 1, mode 2, mode 3. In Raman spectra, we'll talk about the scattering of light, like Stokes lines and anti-Stokes lines. Okay. So it indicates that like how much of light gets scattered, depending on that intensity will vary. If there is a more scattering, it is more intense. If there is a less scatter, less intense. Depending on that, if the more scattering means the value is high. Okay, these are the like values. So now let's try to draw the spectra here. So before drawing spectra, let's consider. So here you can visualize, you can animate your structure. You can visualize what kind of vibration is going on. Okay. First, I will talk about these IR spectra. Then we'll go the Raman, all those kind of spectra. See, when you talk about the IR spectra, there is a different types of vibrations, right? Like stretching is there, bending is there. And in the stretching, we consider two types, like symmetric stretching, asymmetric stretching. And when we talk about the bending, there are 4 different types of bending, right? Like wagging, twisting, all those kind of like scissoring is there. Okay. And now we can visualize what kind of vibration it is. So this is the first mode. Select this first mode. Okay. That is 241. And once you have selected this one, you just click on the start animation button. Once you click on the start animation button, see, it will start. See, you can visualize how the structure like vibration is going on for this mode. Okay. This is the intensity for that one. This is the frequency. Okay. This is the frequency, how much like wave number you are getting, frequency. And this is the your intensity of that peak. And even if you want to show the like vector in which direction it was going, in that case, what you need to do here, you just check this button, like show displacement vectors. You just activate this button, show displacement vectors here. See, now you are getting the vectors also. It was giving the direction also, what kind of direction it was. See. And even if you want to increase the scale of that vector, you can see you can increase it or decrease it. And like if you want to save this one, even like if you want to increase the speed, you can just increase this one. See, now the speed got increased. Like this is the displacement. Now it was movement is more, right? If you decrease the displacement, it won't. Slightly it was like going. The displacement is amplitude is very less. Okay. See here. And if the speed, if you want to increase like number of frames, okay, for cycle, even you can just increase this one. Like you can make it like 100. See, very slowly it is going. Let's consider 10, very fast. Okay, even you can play with the speed of these things. And if you want to change the word like different model, already you know that how to change represent in different models like a ball and stick wireframe. You can just do that one. But let me keep it as like 40 only. Okay, and now even you can make the video of this. Okay, you can make the video of this. So you can save it as video and you can use it for your PowerPoint presentation, or you can use it for your graphical abstract, all those kind of things. Let me show, like even like if you want to visualize your nest mode, you just click here. So this is your nest mode. Like see here. You can just visualize everything here. Like if you want to visualize the OH stretching here, so OH usually it will come at like 3000 something, right? You just click here, see, this one is OH. The OH stretching frequency is this much. Symmetric stretching, that is like 3835. That is the wave number, or you can call it as like frequency. See? Let's consider if you want to save this one. Let me deselect this displacement. If you want to save this one as a movie, how to save this? You just stop this animation. Just stop this animation, and you just, there is an option like save movie. Okay, you just click on this option here. There is two, like there are 3 options are there. One like save movie files. Next one is like save movie frame files, and save both. So what is the meaning? If you say click on this one, save movie file, it will select save only video, the animation part. Okay, and let's consider if you click on this button, save movie frame files, so it will select, it will save all the images. It will save your both video and the entire video as the images. Like here we have given the total 40 cycles. It will generate the 40 cycles. Even after like small movement, how the structure of your molecule will like changes. Okay, it will record that one. But no need to save this one. If you click on the both, it will do both. But I want to save only this one, like save movie as file. You just click here, and I will just save it on the desktop. Let me give it name as like only one, and you just click on the save button. See, now it will capturing the frame, and it will take some time, around like 40 to 50 seconds to complete the process. Yeah, it was done. Now let me show it here. See here, it got saved here. So this is the one what I have saved. Now just open it. See, Even you can change the background representation, you can label it, everything yesterday you have demonstrated you can do the modification, whatever the modification you want. And now you can use it for your PowerPoint presentation, or if you want to, if you're like a teacher, if you want to teach like in a interactive way, you can use these kind of things. So student will like this. Okay, so now just let me close this one. Now come back to your software. Optimization file. Okay, logarithmic file. Okay, so let me open once again this, go to the results, go to the vibrations, right? I hope it is clear to you. And now, how to generate the spectra, like how to generate the IR spectra, how to generate the Raman spectra, how to generate the B.Sc spectra. It is very simple. At the bottom, you have the option, like third option, spectra. You just click on the spectra option. See, once you click on the spectra option, it will give the your generate your spectra. Let me hide other plot. See, this is your spectra, IR spectra. Okay, so in the IR spectra, along the x-axis, what we'll take? We will take the wave number in terms of like centimeter inverse. Okay, and along the y-axis, we'll take the intensity. So here it will represent in terms of like D or epsilon. Like that is molar extinction coefficient. Okay, so this epsilon is molar extinction coefficient, and that is a unit value. But we no need to focus about this. Main we want these things. What is the wave number, like frequency values? That is what we want from the IR spectra, right? And what is this wave number indicates that? So wave number indicates that these are the position of the peak indicating the frequency of absorption, where the absorption is going in your molecule. That is the meaning of these peaks. So along the y-axis, you have the intensity. So the intensity will tells the like what is the height of your peak. So the height which is related to the amount of light absorbed. If there is a more absorption of light, more intense will be your peak. If there is a less absorption, less intense peak. Okay. And if you talk about the scale of your IR region, we usually will consider in the like 4,000 to 400 centimeter inverse, right? And there will divide into like two parts, like functional group region and fingerprint region. So we'll consider like 4,000 to 1,500 centimeter inverse as a functional group region. And we'll consider like 1,500 to 400 centimeter inverse as a fingerprint region. Okay. So there is a question from Samruddhi. Okay. So when we do IR, we get the upside down peak. Yeah, that is like, see, in your IR spectroscopy also, if you do the experimental, there is two things. One thing is you can measure the absorbance. One thing is you can measure the transmittance. Okay. If you measure the transmittance, then you will give the downward peak. Okay. Like reverse of this spectra. If you measure the absorbance, then you will get this kind of absorbance spectra. But no need to worry. I will show that one also. You can create the transmittance spectra also. Now it is showing the absorbance spectra. Even you can show the transmittance spectra also. I will show how to visualize the transmittance spectra also. I hope it is clear to you, Samruddhi. And Mohammad Ilyas, I will come back to your questions later. Okay. So here we'll consider like functional group region and fingerprint region, right? So the functional group region is like where the most of the functional group absorbs. Okay. So here the peaks in this region can help us to identify the different like functional groups which are present in your molecular system. Here we have the OH functional group, right? And what does this fingerprint region tells? So this region contains like complex absorption pattern, and it is like unique for each molecule. I think you have studied it. These are like very basic concepts. I think you have studied at your graduate and master level. Okay. So now how you can save this spectra, and there is a according to like different we have scale, right? If there is a like alkane, like CH vibration, then you will get the like your vibration band in the range of like 2,800 to 3,000. If there is like alkene stretching, then you will get like 3000 to 3100. If there is an alkyne, 3000, like 3300 around, you will get, right? If there is a alcoholic phenolic OH will be there, you will get in the range of like 3600 to 3650. Those are some ranges you will be there. You will get those information in the textbooks. I'm not going to talk about all those kind of things. And now see here, if you want to save this spectra, you can save it here. Okay. So you just right click and you can just, if you change the properties here, okay. First, I just want to, before saving, I want to show the properties here. You just right click and then go to the properties here. Once you click on the properties here, so this window will pop up here. Okay. So here you can change it here. Let's see, you can how to unit. If first, let me, there are like different tabs are there. First, you just click on the plot tab. And there is a first option is unit. Either you can represent in terms of like centimeter inverse, nanometer, gigahertz, this tetra or like terahertz. I think it is like terahertz, and you can scale by, can give any specific that one. So usually we'll represent IR spectra in centimeter inverse, then go with the centimeter inverse. And if you want to invert, so usually what we'll do while doing this IR spectra, we'll consider from this here, right? It will go from like 4000 to 400. Now it is like reverse, like 0 to, if you want to inverse your spectra, you just click on this inverse axis. See, now it was starting from 4000 to this one, and it was changing here. I hope it is clear to you. So usually this kind of experimental spectra will get when you do the experimental analysis. It will start from 4000 to 400. See, this is for the OH. So this is like functional group region. So, sorry, fingerprint group region. This is a functional group region here, like from here to here. You can inverse the axis also. And origin also you can start. From where to start? Origin. So usually our spectra will start from 400. You can keep it as like 400. Let me 400. Okay. See, now it was starting from the 400. Let me fix a range. Origin is from 400. Okay. Yeah, now it is starting. I think 400 origin minus 400 taking. Let me keep it as 0 only. Otherwise, here you will give the region. Instead of that, you can here also. So fixed region like 4000. Here don't need to change anything. Origin. It is not okay. So you can start it from here only. You just activate this button, fixed range. So our spectra is like 4000 to 400. You can change it here. Now it will show it here like see 4000 to 400. You can represent here. And now like this is for the x-axis. If you want to modify your y-axis, you can just change the unit of your y-axis. There is only one, and there is invert. See here. Now I think you got the transmittance one. If you activate this inverse axis of your y-axis, you will get the transmittance kind of vector, like how you will get experimentally. I think Samruddin, I think now you are happy, right? So you can use this option. Just you have to invert your spectra. And here also you can fix the range, like if you want to intensity, but here no need to change anything here. Okay. And just come to the title option here. Once you click on this title tab here, you can give the change the title. If you want to change this IR spectrum title, if you want to give any other specific name, and you can just mention it here. And if you want to change the title color, you just select it here and you can just change the color of the title and it will change the color here. And even you can change the font style. Here, if you click on the font, you can just change the font style, whether you want to keep like normal, bold, or italic. You can just font size, everything. You can just, if you want to underline, you can do a lot of things here. I'll just click on the OK button. And even like x-axis, y-axis, you can change your x-axis title. Now x-axis is like frequency, but usually will represent in wave numbers, right? So you can just write wave number. And then like y-axis, what you are going to do. So you can just consider y-axis is like intensity. Done. So y2 axis is there. So y2 axis, if you want to change, like now it is like intensity. And if you want to give some kind of like y-axis intensity, you can just change that one also. And the axis title, like color also, if you want to change, you can change. Let me keep it here like a. See. So there is a question from it, like what are the practical applications of DFT calculation? So DFT calculation itself is a theoretical calculation, right? Then what are the practical application? So practicals means, I don't know you're from which background. Can you mention it? What is your background? Whether you're from physics department or chemist, and what exact, like what you are doing now? So whether a research scholar or like you are a bachelor or master student. And please mention your name because it was showing IT only. So like when we talk about the practical, it will comes like experimental results, right? So in the DFT calculation, what happens? We are going to calculate the theoretical studies. We are going to do the theoretical studies. Okay. So based on the theoretical algorithms, functional basis, we are going to calculate the different properties. So it won't give any experimental data. But what you have to like, let's consider theoretically you are getting this IR spectra. And experimentally, you just synthesize your sample and you just measure these IR spectra experimentally and you can compare it. And you can just make sure that you can supplement your experiment data with this theoretical data. And even if it is like new material and if you're not able to identify like which peak is corresponding to which one, then also these kind of things are helpful, these theoretical spectra. I hope it is clear to you. So, Suruchi, please provide some basic research publications. Yeah, at the end, I will share the research paper. No need to worry about that. So, I'm Shubhash, I'm postdoc. Okay, got it. Okay, perfect. Yeah, here you can just correlate with your experiment. Okay, like if you want, whatever the studies you can do, you can calculate like IR, Raman spectra, because experimentally we can measure the IR spectra, Raman spectra, NMR spectra, UV spectra, and theoretically you can calculate it and you can correlate it. So whether whatever the experimental data you are getting, whether it is matching with theoretical or not. If it is matching, then whatever the material synthesize it, like it is purity is good, and it will like supplement it will validate your experimental studies. I hope it is clear to you, Shubhashri. Okay, so now here you can change the, I'm talking about color, right? Okay, so you can change the color here. You can select it here and you just click on OK. So see, it will change the color of your y-axis labeling. And even here also you can change the font, all those kind of things here. And yeah, you just click on the appearance here. So how you want to show this appearance? The first one is like curve. So if you don't want to show the curves, see, it will go the curve. It will show only the lines. You just click on the curve here. And if you want to show these curves in a different color, you can just choose the different color here and you can just represent it here. And if you want to increase the width of that one, you can just go with like this. Let me give you the 3. See, it will increase the width. And even if you want to like sticks are there, if you don't want to show these sticks, you can just deselect this. So these sticks will go exactly. Okay. And the marker is, if you don't want to show marker, this one is the marker. So what is the use of that marker is, if you keep that marker, it will show like what is your, exactly for which one it was showing this peak. What is the mode like that? You can compare that one. And here, next one is like grid version. Like there is a grid is there, right? At the background. If you don't want that grid, you can just deselect it. Then it will give the, like without any kind of grid. And if you want to change the background color also, you can just change the background color here. See here, but keep it white for the publication purpose. Okay. And now we can go to the numbering also. Like number colors are there, these things number. If you want to change this number color also, let me show it just like red color. You can change the numbering also. Okay. And this like maximum precision, x-axis minimum precision, you can change do that one also. I hope it is clear to you. Like you can beautify your IR spectra. So you have to follow the same procedure. You can do this kind of modification for all kind of spectra, IR, Raman, VCD, but I'm not going to show for all the spectra. I have explained for one spectra. Okay. So there is a question from Shubhashri. Can I do DFT for polymers? Yeah, exactly. Can do that one. Whatever material it may be. Either it may be like organic, inorganic, polymer, metal complex, so like solid material, everything you can use. Okay. So this DFT calculation is applicable for all type of materials. So now, if you want to save the spectra, you just right click and click on the save picture. Okay. And you can save it in which format you want. There is a different formats are there. You can save it. You already know this option, right? And if you want to save this data, you can just click on the save data. You may get the question. Let's consider, instead of keeping these two spectra separately, your theoretical separately and experimentally separately, you can plot both the spectra in same frame. Okay. both your theoretical spectra and IR spectra. In that case, what you need to do, you just right click and you just click on the save data. And similarly, your experimental data also will get the Excel file. When you do this, your IR studies, you will get this Excel data, and both the data you just paste it either to your Excel or like Origin software, or you can use the Gaussian, GNU Plotter. There are many softwares are there, and you can plot both the graph in same frame, and you can just compare them whether they are matching or not. So that will be more good still. Okay, and like this. Okay, now let me talk with other spectra. Okay, so what I will do, I will just IR, I will open the Raman spectrum. See, this is a Raman spectrum. Okay, so what information we'll get from the Raman? So usually this Raman spectroscopy is used to study the vibrational, rotational, and other lower frequency in your molecular system. So it measures the scattering of light by the molecule. So when the light interacts with the molecules, so most of the photons will undergo the elastic scattering, right? Elastic is nothing but we usually will call it like relay scattering. So, but the small fraction of light will undergo the inelastic scattering. So major will go the elastic scattering, but small fraction of your light will undergo the inelastic scattering. So which results in the shift in the energy. Okay, so that energy will correspond to the vibrational mode of the molecule, and it will be shown in terms of like Stokes lines and anti-Stokes lines. The Stokes lines are lower energy scattered light, whereas anti-Stokes lines are higher energy scattered light. This is the like basic theory part of Raman spectroscopy, the basic principle. And you have to keep in mind that not all the vibration modes are like Raman active, right? There are some Stokes lines is there, anti-Stokes lines are there, different types of like scattering and inelastic scattering vibrational modes are there, but not all vibrational modes are Raman active in nature. Only the modes that can cause the change in polarizability, okay, those are considered as the Raman active. I'm repeating once again, only those vibrational modes that can cause the change in the polarizability of the molecules during the vibration are considered as the Raman active modes. Otherwise, if they are not involving in any kind of like polarizability change, those are Raman inactive modes. I hope it is clear to you. And if you talk about the this ethanol, we have taken ethanol as an example, right? Ethanol is Raman active one. So that's why you are getting the peaks. If it is like Raman inactive, there is no Raman active modes, vibrational modes, you will get just a flat line in your Raman spectra. So now like try to understand like how to interpret this spectra. So usually in the Raman spectra, what we'll take along the x-axis will represent either wave numbers or frequency, right? And along the x-axis will represent the intensity or observance. So then how to interpret? See, you will get like this kind of peaks here, then how to analyze this one. So here, the intensity, you have to focus on these intensities here, intensity of the peak. So here, the intensity of your Raman peak corresponds to the amount of scattering, how much scattering is taking place there. So which can be related to the concentration of the scattered molecule. If the peak is more intense, okay, so the more intense peak indicates the higher concentration or greater Raman scattering efficiency for the specific vibrational mode, that particular vibrational mode. If there is a less intense, it indicates that the less concentration or lower Raman scattering efficiency for that vibrational mode. That is the meaning of this intensity. So what information we get from this height of this peak? And next we have to focus on the width. Okay, so the width of the Raman peak provide the information about like their physical properties, like physical properties of the sample and the environment of the vibrating molecule. Okay, so here you have to focus on the two parameters. What is the intensity of the peak? Another one is the width of the peak and where we are getting the peak. So the position of the peak will give the information about the Raman active vibrational mode. Okay. And the intensity will give the information about the concentration of that compound or like concentration, like percentage of scattering. If there is a more intense, more Raman scattering, less intense, less Raman scattering for that mode. And the next one is the width of the peak. So by analyzing the width, you will get a lot of information about the physical properties of the sample, like what kind of environment for during the vibration. So usually when we talk about the width, we have talked about two terms like narrow width, broad width, like narrow peaks and broader peak. So narrow peaks indicates the well-defined. So well-defined and homogeneous sample with minimal structural variation. That is the meaning of that one, peaks. So if you are getting like broader peak in your spectra, it indicates that there is a structural disorder. Like there is, it may be the amorphous phase is there. Or there may be some interactions like hydrogen bonding will be there in your molecule. Because of that, it may be the broader vibrational mode. Okay, so that is the meaning of that. See, if you see individual peak, like here, like quite more is there. If you compare this one, here it is more. That is for like OH. Okay, so usually you have to keep in mind, if there is, you are getting like narrow peak, it indicates that it is like well-defined homogeneous sample. Okay, so there is a minimal structural variation is there. If you are getting the broader peak, it indicates that there is a some kind of like structural disorderness is there. It may be the amorphous phases will be there, or there be some kind of like weak interactions like will be there, like some hydrogen bonding will be there. So that is the meaning of that. And you can correlate with your application, what kind of application you're going to focus. Okay, I hope it is clear to you how to do the analysis of Raman spectra. Okay, so now let's move on to the and saving, changing like similarly. Just right click here and go to the properties. Here also you can just play with your spectra. Similar like how we have did modification to IR spectra, same procedure, you just go with that. Now just let me go to the next spectra, that is the VCD spectra. Let me close this one. Okay, so now we'll talk about the VCD spectra. See here, we are getting the flat line here. There is no peak, nothing, all those kind of things. But let me talk like how to do the analysis. Before that, let's try to understand what is VCD spectra, then what information we'll get from the VCD spectra. So VCD is nothing but vibrational circular dichroism, right? So it is also one of the analytical technique that measures the difference in the absorption of left-handed and right-handed circularly polarized light. Right? That is what the circular dichroism. So when you talk about circular dichroism, you talk about the like left hand and right hand circularly polarized light by the chiral molecule. And it will act as a function of your wavelength in the infrared region. Okay. So it will measure the difference in the absorption of left-handed and right-handed circularly polarized light by the chiral molecule as a function of wavelength in the infrared region. So VCD spectra will give the information about the circular dichroism in the vibrational transition of your molecules. Right? So here the spectrum consists of like difference in the absorbance of the left and right circularly polarized light versus the wave number or frequency of the IR light. Okay. So that is the meaning here. Like if you consider here, so like you will, it is like plot of difference in your absorbance of left and right circularly polarized light versus either you can consider wave number or frequency of the IR light. See here, like you are considering the frequency or wave number. So here it will give the information about the difference in the absorbance. Okay. So usually in the IR spectra, you will get like peak like this, upward peak, flat line, or downward peak. Sometimes upward peak, downward, you will get like both like positive peaks, negative peaks, and flat lines. That is what the pattern you will get in your VCD spectra. Okay. Only you will get like three types of condition. Either you will get the positive peak means upward peak. Either you will get the downward peak or you will get the flat line. Okay. Sometimes you may get the positive line and flat line. Sometimes you may get the like negative peak and the flat line. Sometimes you will get both positive line and the negative peak. Now, like how to analyze this? What is the meaning of that positive peaks? What information will get from the negative peak? What information it will test like if there is a flat line, right? That is what important. So that is how we can extract the data from those spectra. So let's consider in your VCD spectra, it contains some positive peaks. Okay. So if there are positive peaks in your VCD spectra, it indicates that left circularly polarized light is absorbed more than the right circularly polarized light at the specific wave numbers. I hope it is clear to you. Let's consider here at equivalent to 1000, you are getting like on positive peak here, positive band here. So it indicates that at wave number, this wave number, at wave number 1000, so this absorbance of left circularly polarized light is more compared to the right polarized circularly polarized light. That is the meaning of that. So because here when you talk about the VCD, we talk about the only the difference of absorption between the left and right circularly polarized light. I hope it is clear to you. I'm repeating once again. If there is a positive peak in your VCD spectra, it indicates that left circularly polarized light is absorbed more than right circularly polarized light at that specific wave number. That is the meaning of that. Okay. And here, if there is kind of like negative peak, if you get some kind of like negative peak, down peak here. Okay. So if there is like down peak here, so it indicates that the negative peak indicates the right circularly polarized light absorbed more than the left circular polarized light at that specific wave number. That is reverse of that one. Okay. So the negative peak indicates that the right circularly polarized light is absorbed more than the left circularly polarized light at specific wave number. Okay. And then what is the meaning of there is a flat line? See, for this one, we are getting the flat line. For ethanol molecule, we did the VCD spectra. So here we are getting the flat line. So what is the meaning of that? So it indicates that a flat line in your VCD spectra suggests that there is no significant difference in the absorption of your left and right circularly polarized light at those wave numbers. That indicates that the absence of a chiral center affecting the vibrational mode in your region. And the actual meaning is that the molecule is achiral in nature. By performing the VCD and ECD calculation, we can find out that whether our molecule is chiral or achiral molecule. Okay. So here, whatever we have taken the ethanol, right? So ethanol is achiral. It is not a chiral. It is a achiral molecule. So that's why we are getting the flat line. So because there is no difference in the left and right circularly polarized light absorbance. Okay, I hope that is the meaning of the flat line. So that's why for ethanol, we are getting the flat line. And if you want to get some kind of like positive or negative peak, in that case, you can take any other chiral molecule and you can perform that, you will get the peak also. Okay. So that is how you can analyze the VCD spectra. And if you want to save this one, you can just right click here and you can just click on the save picture. If you want to click the data here, you can just click it here. And if you want to click on the properties and you can change it here and you can do changes here. So and if you have any questions now related to the IR spectra, Raman spectra or VCD spectra, so please write it in the chat box. So there is a question from Amini. So can we do any simple molecule to know about this VCD? No, that is the same thing. That is what I have explained now. So we have did the VCD for the ethanol, but if you want to observe the positive or negative peak, so instead of ethanol, you can take any chiral molecule. Okay, chiral molecule, and you can just do the calculation for DFT calculation for that frequency calculation. You just run it, and you will get the positive or negative peak in your calculation. I hope it is clear to you, Amini. And there is like, so because if I repeat like, once again, if I do the calculation, because again, I need to optimize the structure. So I can't go for direct frequency, I need to optimize. If you want to check now, after this session, you can try it. Okay, those who are interested, you can take like simple molecule like lactic acid. Okay. And in that case, you can just visualize this positive and negative. You can take lactic acid, a simple molecule. So it contains around, what is like lactic acid, like around 3 carbon, 6 hydrogen, and 3 oxygen. There are total 12 atoms are there. Okay, so you can take that one. Lactic acid, you can draw the structure of lactic acid and you can perform the optimization that you will get the spectra. Those who are interested, you can practice with that. And Rakesh, will it applicable only for chiral molecule? Yes, yes. That like see, Rakesh, here we can perform the VCD calculation for both chiral and achiral molecule, but only chiral molecule will give the either positive or negative peak. Your achiral molecule will give the flat line. That is the difference. You will get the VCD spectra, but you will get only flat line. But usually VCD will do to identify whether it is a chiral or achiral molecule. Even by using your theoretical knowledge, also you can find out that. What is the chiral center, whether it is chiral or achiral. If you're good in the stereochemistry, you can do that one. And there is a question from Gauri. if we do frequency calculation in specific solvent, will we be able to see peak broadening or effect of solvent? Yes, you can see that. So because like when we study this IR spectroscopy, there is a different factors which affect the intensity and the width of the peak, right? That solvent effect is one of the major one. And if you want to observe, you can just do it in different solvent. You can compare with that one. What is the effect of solvent on the peak broadening of that molecule? Can take some like 3 polar and 3 non-polar solvent. In that solvent, you can perform the frequency calculation and you can do that one. I hope it is clear to you, Dr. V.S. Gauri. So any other questions? If you have any questions, please write it in the chat box. Okay, so like that, you can calculate the different vibrational spectra. So along with that, even you can calculate the Raman optical activity spectra, that is ROA spectra. But here I'm not going to calculate here because it will take time. But let me tell like what information we'll get from the Raman activity spectra. Okay, so here the Raman optical activities measures the the difference in the intensity of your Raman scattered light when the incident light is circularly polarized, because it will provide the information about the chiral properties of your system. And it will give the information about the stereochemistry of the molecule. Which one? The Raman optical activity. But you have to keep in mind that Raman optical activity spectra is different from Raman spectra. They are not same. Now you may get the question like how it is different from the Raman spectra. So usually the Raman spectra measures the Raman scattering, right? Whereas your Raman optical activity spectra measures the intensity difference. Okay, the intensity difference between the left and right circularly polarized Raman scattering. And similarly, your Raman spectra will give the information about the vibrational frequency of a molecular bond. Whereas your Raman optical activity spectra gives the information about the chiral properties of the 3D structure of your molecule. Okay, and your Raman spectra is not sensitive to the chirality, whereas Raman optical activity spectra is sensitive to the chirality. That is the difference between the Raman spectra and Raman optical activity spectra. When there is a concept of chirality, in that case, we focus on the Raman optical activity spectra. Now here you will get the question like how you can analyze the Raman optical activity spectra. Like how we have the, so there is a question from Anjali, what if it is like both positive and negative? It indicates that in your molecule both. See, if you understand my previous explanation properly, you will get the answer for this question. So what I said, if there is a positive line, okay, so there is a positive line, what does it indicate? It indicates that the left circularly polarized light is observed more than the right circularly polarized light. I did not stop my statement there. I mentioned some other term that at that specific wave number. Okay, that is very important. Let's consider at like 1000, you are getting one positive line here, positive peak here. It indicates that at 1000 wave number at that respective mode, because there are different number of modes, right? Different types of modes are there. At that mode, the left circular polarized light is more absorbed compared to the right one. Similarly, let's consider at 2500, you are getting the negative peak. It indicates that at that respective mode, at wave number, right circularly polarized light is more absorbed than the left circularly polarized light at that specific wave number. I'm mentioning that at that specific wave number. That is the meaning of that. I hope it is clear to you, Anjali. So whether it is clear or not, you have to, yeah, perfect. So let's come back to, I'm talking about Raman optical activity, right? So yeah. So here also, like how to analyze this Raman optical activity spectra. So here also, so it shows the location of chirality in molecule. Yes, perfect. Yes, yes. It will show. So where exactly the chirality is there. So based on that, you can just find it out. Okay. So here also, like how we, in the VCD spectra, how we have like positive peak, negative peak, and flat line. In your Raman optical activity spectra also, you will get like either positive peak or negative peak, or both positive, negative peak, or flat line. So what does it indicate? The flat line are like region with no peaks, indicates that there are no chiral sensitive vibrational modes in those part of the system. Okay, so that is the your molecule is achiral. Okay, if there is a upward peak, like positive peak, it indicates that right circularly polarized light is more absorbed. It means that your vibrational mode associated with the peak scattered light, that is like predominantly right circularly polarized. Like it is similar to your VCD spectra. And the downward peak indicates the left circularly polarized light. Okay, it means that the vibrational mode associated with the peak scattered light, that is predominantly left circularly polarized. That is like how you need to analyze your Raman optical activity spectra, but due to it will take a lot of time, so I'm not going to show how to do, but you will get the spectra like this only. But as our ethanol molecule is achiral in nature, even if you calculate the Raman optical activity spectra for ethanol, you will get the flat line like this. But for the chiral molecule, you will get the positive, negative peaks. Okay, depending on the type of molecule, so you will get the either positive or negative peak. So like that, you can do the analysis of your IR spectra, Raman spectra, VCD spectra, Raman optical activity spectra. I hope it is clear to you. So do you have any questions so far related to this one, calculation and analysis of IR, Raman, VC, and Raman optical activity spectra? So if there are any questions, please write it in the chat box. If you don't have any question, if everything is clear, then type Y in the chat box. Then we can go to the next part. So you have to respond fastly. So we are left with only 30 minutes. So there is a question from Rakesh. If molecule contains more chiral centers, then it shows more positive and negative. Yes, yes. Okay, now let me close this one. We'll go to the next part. Okay, so now let's try to learn how to calculate the NMR spectra, how to perform the NMR calculation. So by performing the NMR calculation, you can predict your proton NMR, carbon NMR. If there is any oxygen in your compound, you can calculate the oxygen NMR. If there is a nitrogen, you can calculate the nitrogen NMR. Okay, you can do all those kind of calculation. Now let me show how to perform the NMR calculation. So for NMR calculation also, we have to open the logarithmic file of your optimization calculation. So not the frequency calculation, we have to use the optimized structure, logarithmic file of your first calculation. So those who are doing simultaneously with me, just open the logarithmic file of your optimized structure. So click on this open, then select the logarithmic file, this one like ethanol underscore opt logarithmic file, and you just click on the open. So this is the optimized structure here. Okay. So to submit the calculation, keep the cursor on your structure and you just right click, go to the calculate and just click on the Gaussian calculation setup. So once you click here, you will get this window here. So here you need to choose the calculation type, different parameters, all those kind of things. So first one is the job type. So you just click here, and now this time we are going to perform the NMR calculation. You just select the NMR. Okay, you just click on the NMR. And once you click on the NMR, you will get directed to this option. The first one is like which kind of method you want to use for the NMR calculation. See, so usually we'll go with the GIAO method. There are like 4 methods are there. The first one is like GIAO method. So GIAO indicates that like short form, like it is like a gauge independent atomic orbital method. Okay, so below that there is a one more method like CSGT. So CSGT means like continuous set of gauge transformation. And there is one more method is there like IGAM method. So it indicates that individual gauge for atoms in your molecule. So it is like CGST, IGST is the combination of these two. But usually we'll go with this one. GIAO method is the best one. For NMR, you just select this one. So NMR, this one is GIAO. By default, it will choose. Okay, you can select this one. And here, no need to choose anything here. You just leave it like this and then go to the method. So method also no need to do anything here. Okay, everything it will take from our previous calculation. No need to change anything. And now just click on the title here. So change the title. So now this one I will give ethanol underscore NMR. NMR, and you just copy the title here. Just copy it. Now just come back to here. No need to change anything. Here also no need to change. No need to change. No need to change. Now we just come to the solvation. It is important here. So how we will do the NMR? So NMR will do by using some solvent, right? Deuterated solvent. But without using solvent also you can do. Because in NMR there is a two types, like solution state NMR and solid state NMR. So if you are going for the solid state NMR, then no need to use any kind of solvent. You can directly use it. In that case, you need to calculate your NMR spectra in gas phase. I hope it is clear to you. Okay, let's consider you are comparing your NMR spectra with the solution state NMR. For experimentally, you can do in two ways, right? Either solution state NMR or solid state NMR. In like experimentally, if you did the solid state NMR and if you want to compare your experimental NMR with the theoretical NMR, in that case, you have to do the NMR calculation in gas phase without considering any solvent. Okay. For example, you experimentally did your NMR spectra by using in a solution state. In that case, you have to use the according to that. Because in solution state, usually in 90% of cases, either you will go with the two solvents. If your compound is like less polar, in that case, you will go with the deuterated chloroform, that is like CdCl3. If your compound is polar, then you will go with the deuterated DMSO, dimethyl sulfoxide, right? Sometimes if it is like insoluble in methanol, like CdCl3 or DMSO, you can opt, if it is like water soluble, then you can go with the deuterated water, that is D2O. Or if it is like soluble in methanol, you can go with the like deuterated methanol, deuterated acetonitrile. There are different solvents are there, deuterated acetone. So which solvent you are using experimentally, theoretically also you can choose same solvent. So, but majority of cases, in cases we go with either CdCl3 or DMSO, and this calculation let me show with either any one of those two solvents. Okay. So here, like these are the different water models are there, but I will go with the default model. Okay. Either you can go with the default, or if you want to use some specific model, you can go with this PCM is like a good model among those, but I will go with this one only, default option. So once you click on this default option, it will show the option to choose a solvent. And you just click here, and now we can choose. See, if you want to go with like DMSO, you can choose this one. Or if you want to go with the chloroform, you can just choose this one. It is up to you. Like for example, experimentally, if you done DMSO, then you can go with the DMSO calculation. If you did with chloroform, then go with the chloroform. If you did with like ethanol or acetone, you can choose according to that. You can choose here. But let me go with the chloroform for this calculation. I'll go with the chloroform. Okay, and then no need to change anything here. Additional input, no need to give. Then click on the preview. So it will create the input file for your calculation. And no need to give any kind of like additional keywords here. Okay. So there is a question from Tejashwini, calculate of Gaussian setup is not open. I think you are not opening properly. Okay. So here you just click on the submit button. So once you click on the submit button, it will ask you to save your input file. Click on the save button, and here you have to provide the name. You just Control V here, because already we have copied this name from the title one. You just paste it here, ethanol_NMR, and you just click on the save button. So once you click on the save button, it will ask you to submit the calculation to the Gaussian. You just click on the yes button. Once you click on the yes button, so it will submit the calculation to the Gaussian, and it will start the calculation. So it will take around 1 to 2 minutes for this compound for the calculation. Okay, see, the calculation was completed. Because usually it will take more time for the optimization calculation, energy optimization, and the frequency calculation. But for NMR, it won't take much time. And for time-dependent DFT calculation also, it will take more time, like a UV energy calculation. But for NMR, it won't take that much time. But it depends on the structure also. If the number of atoms are more, comparatively, it will take more time. But comparative to frequency calculation, it will take less time. So in my case, the calculation was done. So now we'll do the analysis, result analysis part. So before going to the result analysis, so let me confirm that how many of you have completed successfully calculation. So there is a question from Yamini. So can you please show those calculation? Okay. So there is a question from Hardi. Generally, IR is performed with KBR. In that case, which solvent we should select, or simply none option need to select? Okay, I think Samruddhi, are you master student? So how does the time taken scales with the number of atoms? Okay, there is a question from Gayatri, like how does the time taken scales? Yeah, like there is a like no universal factor, but as the number of atoms increases, the time needed to perform that calculation increases, and also it depends on the size of your atom also. Let consider if there is like a atom with like more number of valence electron, that also it will take more number. It won't not only focus on the like number of atom, it also focus on the how many valence electrons are there. Okay, and what is like atomic number of that, depending also parameters varies. Okay, and I will come back to the Samruddhi question. She's asking that because in NMR we use any kind of solvent like deuterated solvent, so you are particularly we are choosing here. But in the IR, usually there is a two type of IR will do, right? One is like KBR, another one is the ATR. So alternated transmission IR will do like KBR or ATR. So our question is like in that case, if you use the KBR, so which solvent I need to use? Whether I need to choose any solvent or simply I can do the calculation. See, first I want to clarify you why we are going to use the KBR during the IR calculation. See, IR instrument is very sensitive and we need only like pinch of compound in milligram, even like 1 or 2 milligram is more than sufficient to perform this IR spectra, to get the IR spectra, right? But we can't make pellet with that. So if you want to make the pellet, you need large amount of compound. So that's why what we are going to use, we are using KBR, like 1 to 2 spatula of KBR, and we are just grinding properly and we are making it as a uniform and we are making the pellet and we are passing the IR radiation. And that IR radiation only detect your compound. What is the functional group, different vibrations which are there in our compound. Now you may get one more question here. So even KBR is also a chemical compound. Even it can detect KBR bond also, right? But the reason for choosing KBR as a like reference material for to make the pellet is whatever the vibration, KBR vibration it will give, it is behind 4000. Okay, because what is our FTIR range? It is like 4000 to 400. But in that range, we won't get the KBR vibration. So for that reason, we are using the KBR. Otherwise, you will get that. Why we are not using the NaCl? Why we are not using the sodium bromide, right? So that is the reason, because those will give your like a vibrational band in that range, but KBR won't give. For that purpose, we are using the KBR. But here, no need to choose any kind of things because the KBR is not. There is the like involvement of KBR is nothing in our compound spectra. So that's why we are not choosing any kind of KBR. Okay. But in ATR, what we will do, ATR, it is a solution state. KBR is a solid state IR analysis, but ATR is a solution state analysis. Now you may get the question. So in ATR, like how, now which solvent we have to use? See, even when we use the ATR, what we will do if your compound is liquid, and we'll take only pinch of like, even like you can consider, even if you take one drop in that, you can just make like 100 part and you can take one part of that. That is more than sufficient for the IR analysis if it is a liquid compound. But sometimes what we will do in ATR, if your compound is solid, we dissolve that compound in like specific solvent like chloroform, acetone, like that in solvent, and we'll do that one. In that case, you may get the question. So now if you do the IR analysis in that case, you may get the peak for which is related to your chloroform or acetone, whatever the acetonitrile, whatever the solvent you're going to use. But if you have the experience by doing practical experience by doing this IR experimentally, so after like what we will do, we'll take let's consider you are going to measure by using the acetone. You will take the small amount of acetone, let's consider 0.5 ml. In that you are going to add the pinch of your compound. You are making the solution. So now you are putting the one drop of solution on that ATR like surface. But here what we will do, first once you make the drop, we are going to evaporate all the solvents which are present in that compound. So because we are going to use the volatile solvents, particularly we'll use like acetone, chloroform, dichloromethane, like we are usually use this NXN, like very volatile. And if you keep it for some times, like 30 seconds to 1 minute, the solvent will get evaporate. Okay. And it will form the very thin layer of your compound. And now it will detect only your compound. So in that case also, you no need to check that. Let's consider. So you have taken the non-volatile solvent. So you just kept the droplet and you just measured the IR. In that case, you need to perform your IR spectroscopy in that respective solvent. You have taken the DMSO as a solvent. DMSO is a non-volatile. So now it will give in IR spectra, you will get the peak for both for your compound and for the DMSO. In that case, you have to choose the DMSO. Okay. I hope it is clear to you, Samruddhi. Okay, perfect. So now just confirm me that how many of you completed the calculation? So those who have completed this NMR calculation, please type Y in the chat box so we can proceed with the analysis part. Okay, let's start the analysis part. Yeah, you know already these things. Now I'm not going to talk about it. You just click on the S button. So once you click on the S button, you will get this window. You just open your this file. Okay, and you just click on the open button, logarithmic file we are opening. And now here you just click it here and right click, go to the results and then go to the see, whenever you are going to perform any kind of calculation by using the solvent, so this option will be created like PCM solvation energy cavity. If you click here, so it will create the cavity like solvent cavity, how the solvent is there surrounded to your molecule. And you can just let me show it in different color, then you can visualize properly. Let me go with this green one or blue one. See here, pink one. Yes, see. So you can visualize this is like solvent cavity, how the solvent cavity is created. So you can visualize this kind of diagram whenever you are going to use the solvent. Let me close this one. Right click. So go to the results, then click on this. I think I have closed the log file. Let me open the logarithmic file of this calculation. Open. So let me open the logarithmic file of NMR calculation. Yeah, I think it was saving in a different location. Okay, my calculations are saving in different location. Let me find out the path where it was saved. Go to the C drive. So just, okay, let me edit. Yeah, this is the desktop, right? CHK opt, opt, frequency, CHK, NMR. Yeah, so NMR logarithmic file, okay. I just click on the OK button here. Yeah, this is my output file here. Okay, and now just right click and click on the results and then go to the NMR. See, once you click on the NMR, so it will give the your NMR spectrum. So now you can just do the analysis part. Okay, so in NMR, what we will get? So it will determine the overall structure of your chemical compound by examining the magnetic property of your atomic nuclei. So I'm not going to deeper into that part. So because by performing the DFT calculation, so you can calculate what is the chemical shift, what is the coupling constant. Okay, and the area under your each signal in your NMR spectra is proportional to the number of nuclei contributing to that signal. And even you can get the all information related to how the spatial arrangement is there in your system. Okay, so see here, now it is a mixture of all the spectra. Now just let me enlarge this one. So because in NMR, so there is more than like 1,000, not 1,000, I can't say 1,000. There is like more than like 100 different types of NMR are there. For each element, you can perform the NMR spectra. Like in the periodic table, how many elements we have? 118 elements we have. For all the 118 elements, you can perform the NMR spectra. but that nucleus should be NMR active. Okay, that NMR activity depends on the what is the spin of that one. Now here, consider here. So in our molecule, there are total 3 types of elements, right? This one is like carbon, oxygen, and hydrogen. So for hydrogen, we can perform the proton NMR spectra. For carbon, we can perform the C13 NMR spectra. For oxygen, you can perform the oxygen NMR spectra, cysteine oxygen NMR spectra. So how to visualize one by one? So now it was showing all, right? So this is for like oxygen. This peak is for the carbon. So because there is only one oxygen, it will give the one peak. There are 2 carbons are there. This one, it is giving the 2 carbon peak. There is like hydrogen protons are there. Total 4 protons are there, and it will give the 4 peaks here, right? So here, but let me show how to visualize them individually. So to visualize them individually, as a like separate proton NMR, like carbon NMR, or like oxygen NMR, in this element option, you just click it here. See here, there are 3 elements are there. That's why it is going to 3. If there are like 10 different elements are there, then it will give the NMR spectra for all the elements. Okay. So first one, let me go with the proton. You just select hydrogen. And now here, like reference, you have to choose the reference. So usually like none, it won't consider any. But when we do this experimental analysis, we'll consider like TMS as a reference, like tetramethylsilane, because how it will be added, already it is added like small percentage, like usually 0.03% of TMS is added to your solvent. Why? It acts as a internal standard. And why it is used as the internal standard? There are like different reference compounds. There are different is like because it is a volatile, it is chemically non-reactive. It's not that much reactive with any other compound. And whatever the, because a tetramethylsilane means a silicon in the center and it is connected to the 4-methyl group. So there are 4 methyl means each methyl group has 3 proton, 3 into 4, there are 12 protons are there. And for all 12 protons collectively, it will give the only single peak because all the 12 protons are chemically equivalent. So they will give the only one peak. And you will get the peak at the chemical shift value like ppm, 0 ppm. So that's why we are choosing the TMS as a reference compound while we do experimental analysis. So here you can choose this one. There are 3 options. One is none, you are not considering any kind of. Even experimentally also, you can get the solvent, like CDCl3 or other solvent without TMS also, you will get the solvent. But if you're using without TMS, you can, in that option, you can use the none and you can compare. If you're using TMS as your reference standard, then you can choose these 2 options. So now this TMS HF is like Hartree-Fock method, and this one is the your DFT method. We are using the DFT method. Choose this one, DFT method. Now see, when I choose, there is a little bit change in the chemical shift value. So if I choose none, see now it will shift here. But now see here, if you see the chemical shift value, it was like 24, 25. But if you observe the experimental NMR spectra, proton NMR spectra, the scale of your proton NMR spectra varies from 0 ppm to, it will be like around 12 ppm maximum of compound, right? If there is like NH peak is there, OH peak is there, in that case, you will get, depending on the neighboring group, you may get the peak like SH peak is there, like thiol peak. In that case, you will get the peak around like in between like 12 to 15, 16 ppm also. But let's consider maximum 16, 0 ppm to 16 ppm. But here, these protons, because for this ethanol, usually this CH3 and CH2, it will become below 4 ppm. Maximum, it won't go 4.5 ppm. Because there is a theoretically, you can find out, theoretically you can know that what is your different ppm scale. If you are from chemistry background, you know all those kind of things. And if it is a OH proton, it should become in the range of 10 to 12 ppm. Usually you can consider like 9.5 to 11.5 ppm. But if you see the scale here, it was showing it because we have not chosen any kind of reference. So now if I change this one reference here, TMS, see the scale will change it. See how it is changed. Okay. So here, if you observe here, this reference. So here reference indicates that this peak corresponds to your solvent one. Okay, sorry, reference one, not solvent one, that is a reference one. So this one. And if you come to the peaks here, see there are total how many? There are 1, 2, like 3, and there are 5 protons are there. And see we have the different peaks here. So here, these two protons. If you click on this peak, see once you select this one, so it will select those 2 protons corresponding to this peak, because these 2 protons are equivalent in nature, and like they will give the singlet peak here. because you know that, right? I'm not going to talk about like how the multiplicity splitting will take place because it's a huge theory. I'm not going to talk about that. So because these two protons are equivalent, it will give as a singlet peak here. And remaining these protons are there here. And if you click it here, see, it will select this one. And here, actually here it is giving, but theoretically we'll get the single peak, only this one. And like this one is like, I think, OH peak. So as this one is aliphatic attached, this OH is attached to the aliphatic group, that's why you will get. If it is like attached to the aromatic, it will be in the range of like 9 to 12, 12.5. So like that, you can compare, get your proton NMR spectra, and you can compare with your experimental spectra. I hope it is clear to you. And similarly, you can select your carbon. So carbon spectra also, you can get to measure like how many carbons are there, what is the nature of that carbon, you can find it out. And here also, if you choose none, see, it is here. And but you can know that, right, in the C13 spectra, the chemical shift scale varies from 0 ppm to 2000 ppm. Okay, so if you choose this one, but here the values are showing that in the like around, this one is like around 135, and this is around like 175. But this like methyl proton and CH2 proton, CH3 proton and CH2 proton, it will come in the range of like below 20. Okay, like in the range of like 10 to 30 maximum, but it is not showing it properly. You choose the TMS here. See here. So it is this CH3 proton like this one. You just select this one. See, this one is coming at the range of this ppm value here. At the, it will show exact location. It is show here. It's like 7.76 ppm. Degeneracy, it will show. Degeneracy 1 is equal to, like we'll talk about like whether it is a singlet, a doublet, triplet, quartet, multiplet, pentet, like that. So if the degeneracy 1 is equal to, it is a singlet. Similarly, if you CH2, so because it is attached to this oxygen also, so because of this value is increasing. Otherwise, if there is a normal CH2 attached to another C carbon, usually it will come below like 30 only, in between like 20 to 25. And this is like this carbon. So like that, you can just do the analysis. Here also, you can save the spectra by right click, save it, and you can get this NMR summary also here, like all those data, and you can use it for the origin for that. And you can change the properties, like you can change the different properties, color, you can modify your spectra also. Okay, and similarly, you can get the oxygen spectra also. Just select it here, and you just click on the oxygen here, and it will give the oxygen. There is only one oxygen is here, it is giving here. And you can choose this one and go with the water here, these things. And this is your oxygen spectra. So like that, you can just calculate the different NMR spectra. Okay, either it may be a proton or carbon, oxygen, nitrogen, any other like boron, silicon. There are different types of there. You can calculate them according to your requirement. I hope it is clear to you. So do you have any questions so far related to this NMR spectroscopy calculation? If you have any questions, please write it in the chat box. If there are no questions, if everything is clear, then type Y in the chat box. So there is a question from Rakesh. How to get P31 NMR spectra? Same procedure. You just draw your compound here, submit the calculation, it will give the P, proton NMR. Because already told that, so whatever the different types of element is there, it will give. In our element, in ethanol, there is no phosphorus, right? So no phosphorus, that's why we don't give the phosphorus NMR spectra. If your compound contains phosphorus, then it will give the P31 NMR. If you want silicon, if your compound contains silicon, then you will get. So there is a question from Sachin Kumar, how to get the 2D NMR, sir? So here you won't get the 2D NMR, only 1D NMR only. So because in NMR, there are different types of NMR, like one-dimensional NMR, 2D, 3D, and 4D NMR. Okay, but by using DFT calculation, we can find out only the 1D NMR. Because 2D, 3D, 4D are like complex process, we are not going to find by theoretically. You will get only 1D NMR. Any other questions? Depth NMR also we are not going to get here. Okay, so depth NMR means what? Here, like you can find out the type of carbon, whether your carbon is like primary carbon, secondary carbon, or tertiary carbon. Okay, so how many proton is attached to that one? You know, depth NMR, we will do this depth NMR at different angle, like 45-degree angle, 90-degree angle, okay, 180-degree angle. So 3 degree different angles we will do the depth NMR experimentally. And depending on that, we'll find out whether it is like primary carbon or like secondary carbon or tertiary carbon, depending on this peak. Okay. So, but here we won't find the depth NMR. I hope it is clear to you, Sachin Kumar. Yes. Okay. So, any other questions? If there are no questions, if everything is clear, then you just type Y. So we can proceed with the next part. Let me check what is the next thing in the brochure. So let me close this one. So we are done with the day one here. Calculation of IR spectra, Raman spectra. Okay, pre-resonant, Raman optical done, vibrational done, NMR done. So here pre-resonant Raman spectra is nothing. You can do this calculation by using the Gaussian directly. Okay. There is a question from Subhashri. Is there any website to get the polymer structure? So Subhashri, polymers means like what kind of polymer you are focusing? Like there is a polymer, even you can consider like organic polymers are there, right? If you want like monomeric unit or like what? Monomeric unit, you can download it from by PubChem also, or you can download it by using different ICSD database you can download. If it is come to the organic polymers. Yeah, monomeric unit you can download. You can download it from the PubChem database also, Zinc database also. I can download it from ICSD, some structure, you can download it. Otherwise, monomeric unit is quite simple to draw. You can draw it from also. Okay, so we have covered everything. So pre-resonant spectra, I think I didn't talk about this one, right? Pre-resonant Raman spectra. So you can calculate this by using the Gaussian. For that, you can create the input file and you can submit the calculation. I will show how to prepare the input file further at the end while I explain how to submit calculation by using this one. So, but let me tell what is this pre-resonant Raman spectra. So there is a question from Sachin Kumar. So these spectra are matching to experimental spectra. Yes, it will match. If your compound is correct, if your compound purity is good, then definitely it will match. So matching means not 100%. Sometimes 100% matching will be there, some percent like 90% will be there, but not exact. That is what I am telling, not 100% matching. You can consider 70%, 70%, 80%, 90%. Sometimes there will be 100% matching also. Okay. But you have to consider. And one more thing is you have to consider like matters, like what kind of parameters, even like in NMR experimental, if you do, if the compound's having 99%, 90, yes, if it is like that much of purity, yeah, at least you can expect like 90% of similarity, 90% to 100%. Like if the compound is like very simple, the matching will be more. If the compound is like more complex, in the theoretical, what it will do, by using the theoretical parameters, it will calculate what is the expected value. Okay. But it will match. So in my case, the matching will be like 90%, but it depends on like purity, all those kind of things. So please give the idea about that. Yes, I will talk. I will come one by one. Okay. So here I am talking about the pre-resonant Raman spectra. Bhargav. So could you teach how to draw the structure like A3B2X9? And if there are both organic and inorganic atom, I need to choose two basis set. Then how to choose, then how to do that. See, here I will show you how to choose the multiple basis set, but I'm not going to show you how to draw this kind of like layers like A3 or B2X9. For that, yeah, Origin is not, this Gaussian is not a preferable software. For that, you can use either a Vesta tool or you can use the Burai software. Okay, you can use that. Because in this workshop, we are mainly focusing on the organic compounds or metal complexes or inorganic like organometallic complexes. We are not going to talk about the solid materials in this workshop. So in our last workshop, we have because for this kind of materials, Quantum Express Burai is the best software. In our last two DFT workshop, we have discussed these things only, like how to prepare these layers, counter like adsorption studies, catalysis studies, all those kind of things. So there is a question from Subhashri. If I am modeling a new material, what parameters should I consider to check the stability of the material? I want to check whether the material can I synthesize experimentally or not? So parameter is nothing. You just draw the structure. Okay. You just draw the structure. And depending on that, what kind of atoms are present, whether it is organic or metal complex, you can choose the proper basis set and functionals and DFT type of calculation, and it will give the what is the energy. From that, you can check the stability. Okay. So there is no specific parameters. It depends on like what kind of material it is. So on that, I think on first, not first day, yesterday, I think on first day also and yesterday also have demonstrated how to decide this depending on the material, how to choose the functional basis set. Based on that, you have to select it. I hope it is clear to you, Subhashri. Okay. So yeah, when it comes, just I will give you what exactly this pre-resonant Raman spectra. I just within I will finish it in 1 minute. So here, like pre-resonant Raman spectroscopy is like variation. So where the incident light is tuned close to the, but it is close, but not exactly at the electronic absorption band of your molecule. So because of that, it will enhances the Raman scattering cross section and the intensity of the specific vibrational mode. Like, so whatever the information you will get from the Raman spectra, it will give the same from the pre-resonant spectra, even it is not no need to perform this pre-resonant Raman spectra. But the thing is, the only difference is it provides like more sensitive detection. Okay, so it will give more like more sensitive detection of certain vibrational modes, especially like those which are associated with the electronic transition. In that case, it is useful. Otherwise, you can go with the Raman one. So there is a question from Bhargav. After drawing them, can I do the calculation with the file in the Gaussian? Yes, you can do the calculation. But as I told that, in that case, you have to use the multiple basis set. You have to prepare the proper input file. So that is the difficult part. You have to prepare input file properly. If even there is a small mistake in your input file, your calculation will die. Okay. So you have to choose the proper functionals, proper basis set. Okay. But I will give the idea how to choose the in that case how to choose the basis set at the end. I will show you. But you have to be patient. Okay. We are going step by step. First, you have to learn everything basic properly. Then you can go to the advanced level. So now I think we are covered these things. Let me come back to the third. What is there? Calculation and analysis of UV spectrum. Okay. So we are done with already. It is 11:30. So if I start this UV now, it will take around like 20 to 25 minutes. So can I extend it for like another 20 to 25 minutes? So if you're okay, then we can go with the UV spectra. Otherwise, we can continue tomorrow. It is up to you, but you have to respond fastly. So should we continue? Should we stop? So there is a question from Sachin Kumar. So I have one doubt, sir. Like, can I continue Gaussian calculation that are stopped by system showdown like this? So system showdown like means like shutdown, system shutdown. So how you submitted your calculation, your system got shut down, then you can continue. Again, you have to start from the beginning. Okay, you have to start from the beginning. So that is what, because these Gaussian calculation, like not Gaussian, like DFT calculations are highly time consuming process. That's why whenever you are going to submit the calculation, you have to make sure that you have like a specific system. It is completely dedicated for that calculation, and it should be connected to the UPS, and you should have to maintain that system in the AC condition. Because even if you did not mention AC condition, if there is a UPS connection is there, because the calculation will go for like 1 week, 2 weeks. And once your system gets heat up, automatically your system will it will do the restarting. Again, your calculation will die. Okay. Again, you have to start from the beginning only. Okay. So most of the participants, they are telling, I will continue from tomorrow. Okay. We'll do it tomorrow. Okay. No problem. We'll do it from tomorrow. So tomorrow I will try to finish this part, calculation, this, everything. And I will try to cover 50% of this only, because we are done with 3 days. We are left only 2 days. In 2 days, we have to cover everything. So tomorrow I will go a little faster. Okay. Now, if you have any questions, please write it in the chat box. Okay, so I will give 5 minutes, whatever the question you have. So please write it in the chat box. Okay, if there are no questions, so Mohammed, so you're asking again like 2D structure. I already explained, right? So at the end, I will give the idea. It is not possible to run the 2D structure optimization of 2D structure here. Till wait till the last day. So from the Bargos, I tried to with the 2D two basis set. It took a lot of time, around 3 hours. Yes, even 3 hours is very small time. Okay, for DFT calculation, even it will take 1 month also. If your structure is very big and you are using it in a normal laptop or like, it will take a lot of time. So there is a question from yes Gauri. Is this Gaussian software license? Can it be used for? Yeah, you can use it, but it will be active for only some few days only. Okay, so because you have to purchase, if you have license from your institute, you can use it. Otherwise, you have to purchase the license. But for some days, you can use this one. So will it be possible to upload structure directly from online? Yes, you can upload it. Already have shown, right? I have shown you how to upload the structure directly from the online, Rakesh. I think you just go to the day one recordings. So at the end of day one, I have explained like how to upload the structure directly from the this one. So there is a question from US Gauri. How about Orca? Are the results comparable? Yeah, Orca is a free software. You can use the Orca and Avogadro software to perform the DFT calculation. Yeah, it is comparable. It is not mandated that you need to use a Gaussian only. There is a free softwares are there. So what I will suggest, if you don't have the Gaussian license version, if you don't have the, usually Gaussian will be more preferable for organic molecules or metal complexes. And when it comes to the 2D materials, like big solid materials, either this quantum espresso, Burai, or WASP, those are more preferable. Then WASP also is like license version, like a commercial software. So what I will suggest, if you don't have the facility for that license version, for organic molecules, you just go with the organic molecules and metal complexes, you just go with the Orca and Avogadro software. If you have like solid materials, like 2D materials, in that case, the best option is the Quantum Espresso and Burai. That is more compatible. So can we use the same basis set and functionals? Yes, you can use it. But software to software, some basis sets are, because when we choose the software, some specific basis set they have. Because you won't get all basis set and functions which are available in the Gaussian. Okay. But like major, these B3, LYP, PBE, those are available. You can use that one. But when it comes to 2D materials from quantum mechanics, we will consider one more factor, that is pseudo potential. So that is also matters when it comes to the 2D materials, because this workshop is mainly focused on the organic molecules or like metal complexes, not 2D materials. So any other questions? Okay, so if there are no questions, I will end the meeting. Okay, there is one question. Is this Gaussian software enough for publication to show the comparison of results? Yes, it is enough. Any other questions? Okay, I think there are no questions. I'm going to end the meeting. Okay, thank you so much for your patience and be in the class. Okay, bye-bye. Good night.